In the third part, I will introduce the dynamic model developed in this thesis. The model is developed step by step from a one-bank model to a two-bank model, and finally to a multi-bank model. Here I will only introduce the multi-bank model, as it contains all characters of the one-bank and two-bank model. The basic structure of each bank is shown in this figure, which contains 5 activities: deposit, interbank borrowing, investment, cash, and interbank lending. The net worth of the bank is the difference between the asset and the liability. The links between any two banks, I and J, are made of interbank loans and borrowings. A parameter called link rate has been developed to represent the average proportions of links of any bank. The link rate takes values between 0 to 1. The higher link rate, the more links in the network. The behavior of different bank components will be described by differential equations, prescribing the dynamics of the system. Next, I will explain the time evolution of each bank components. This is the differential equation describing how cash changes with time. The first term is the change in cash due to the deposit. It is positive because any increase in deposit will increase the cash, while any decrease in the deposit will decrease the cash. The second term is the change in cash due to investment. It is negative because banks use this cash to do the investment. The third term is the interest rate. It is the interest paid by the banks to depositors. It is negative because paying the interest will decrease the cash. Similarly, all the terms with positive sign represents the money that goes into the bank, and those with negative sign represents the money that goes out of the bank. Importantly, when the cash becomes negative, the bank fails and is removed from the system. The deposits are assumed to be assigned by an exogenous signal, which introduces shocks in the system. Fluctuations in the deposit are caused by random payment or withdrawals of the depositor. In the homogeneous case, DI is the total deposit of bank I. It is equal to the D bar, which is the average size of the deposit, plus a random shock. Sigma D is the amplitude of the shock, and epsilon T is the random variable, which is normally distributed. While in the heterogeneous case, the average size of the deposit of any bank I is assigned by sampling from a Gaussian distribution with the mean equal to mu s and the variance equal to sigma s squared. Fluctuations in deposit may force the banks to borrow money to meet the reserve ratio requirement. This is the differential equation shows the current change of borrowing between two banks. The first term in the right-hand side equation is the amount borrowed by bank I from bank J over time dt. This amount should be the minimum value between the required cash of bank I and the available cash of bank J. This minimum value needs to be multiplied by the parameter sigma ij, which represents the connection between bank I and bank J. This is to ensure that the borrowing only happens between the two banks that are connected. If the two banks are not connected, which is when sigma ij equal to 0, then there is no borrowing. The second term in equation is the proportion of the total borrowing repaid per unit time. When a bank fails, it cannot repay its borrowing to the other banks, and it cannot receive previous lending back from other banks. Therefore, to make sure the repayment only works for the survival banks, the repayment term needs to be multiplied by the parameters SI and SG. which represents the mode of the bank. If one of the two banks fails, then there is no repayment. In the multi-bank model, the interest rate for borrowing and lending changes with time according to this equation. H0 is the basic interest rate applied for lending and borrowing. This can be thought of as a base interest rate determined by an exogenous monetary authority. The second term is the premium charged depending on the health of both borrowing and lending banks, which is measured with BIG divided by CG. BIG is the total borrowing of Bank I from Bank G, and CG is the total cash of Bank G. This figure shows the behavior of HIG for different values of BIG divided by CG. When BIG divided by CG equal to 0, the interest rate is close to H0. When BIG divided by CG goes to infinity, the rate becomes H0 plus A, which is the maximum value possible. Therefore, as the BG divided by CG gets larger, the lending bank faces more risk that it needs to charge higher interest rate. That represents the speed of transaction between the states. The larger values of that, the faster interest rate switches. This is the differential equation describing the investment behavior of Bank I. Each bank makes its investment at time t depending on two factors. One is the cash availability, which is described by these terms here. It is the cash above the value required by the reserve ratio after interbank lending. The second factor is the stochastic investment opportunity at time t. This is described in the second equation. It assumes that the investment opportunity changes randomly around an average value. Omega represents the proportion of the total investment that has matured, and V represents the proportion of total investment that has been lost due to default. This flowchart shows how the bank activities take place during each time step of computer simulation. At the beginning of each step, the bank's cash changes due to stochastic shocks in deposit and interest rate payment. Each bank repays their interbank loans in cash. Those banks that cannot meet the repayment obligations will need to borrow from other banks. Banks that still have extra cash will invest. The banks left with negative cash are deemed to be in default and are removed from the system, and their remaining assets are distributed to depositors and to lending banks. After any default liquidation, a new simulation step will start. At the end of each simulation, the banks that survived are counted and other relevant quantities are calculated for further analysis. Before looking at the result, let's have a quick look at the model implementation. The model is implemented using MATLAB Simulink. This figure shows the top level of the model in Simulink. The red blocks are the external signals inputted into the system, and the yellow blocks are the parameters. The blue blocks are the output result. The fourth part will show some simulation result of a system that contains 50 banks. This is the first result I want to show. We ran different simulations with different reserve ratio and link rate. The simulation time is 300 days. At the end of each simulation, we count the number of surviving banks. The x-axis is the time and the y-axis is the number of surviving banks. Different colors line represents different reserve ratio. This figure shows how the number of surviving banks is affected by different reserve ratio when the link rate LR is fixed and the shock amplitude is equal to 0.3. In the first figure, when there is no interbank lending, the reserve ratio definitely plays a positive role to preserve the stability of the system. As the reserve ratio increases, more banks survive to the end of the simulation. While in the other three figures, when the link rate is not zero, more banks fail when the reserve ratio gets higher. The same trend can be found with the higher shock amplitude, which is equal to 0.7. In this figure, when link rate is zero, a higher reserve ratio makes banks survive longer, while when the link rate increases to 0.15, 0.5, and 1, higher reserve ratio works in an opposite way, causing more banks to fail, because it discourages banks from lending. The negative effect of the high reserve ratio is more obvious in these figures when compared to the figures with lower shock. We can see the space between the lines are larger. The next figure shows the effect of the link rate on number of surviving banks when the reserve ratio is fixed. Different color lines now represents the different link rate. More banks survive as the link rate increases. We see the number of surviving banks increases significantly as link rate increases from 0 to 0.3, and then to 0.15, which is from the blue line to the yellow line, but with higher link rate from 0.3 to 1. More banks survive and not significant differences exist for the different cases. This indicates that when exceeding a threshold value, the increase in link rate does not help much in improving any further of the stability. This trend is more clear when shocks have a higher amplitude. In the first two figures, when the link rate equals to or bigger than 0.3, the increase in the link rate does not make a noticeable difference. These lines clustered together. In the third figure, when r equal to 0.6, lines starts to cluster when the link rate is equal or bigger than 0.5, while in the last figure, this happens when the link rate is equal or bigger than 0.75. This indicates that high reserve ratios limited banks from lending. It is harder for banks to find available cash to borrow as reserve ratio increases. Therefore, banks need to be more connected to have more chances to borrow and survive. We also quantify the contagion using this dynamic model. To quantify the contagion at the end of each simulation, we calculate the proportion of failed banks with significant unpaid loans. If the unpaid loan is larger than the negative cash of the bank when it failed, which means the bank could survive if other banks repaid their borrowing to this failed bank, we then recognize this failed bank has a significant unpaid loans. This figure shows the proportion of failed banks with significant unpaid loans as a function of link rate and reserve ratio. From this figure, we can see both link rate and reserve ratio have non-linear effect on the contagion of banks' failure. The second figure shows the contagion in heterogeneous banks as a function of link rate and heterogeneity. We can see the heterogeneity increases the contagion when link rate gets higher.